Bismillah. Assalamu alaikum, and welcome to our third lecture for the discrete structures. Before we start, I just would like to talk about some general announcements. First, the first one regarding the attendance, because some of you might have noticed that I did not enter the attendance on Edugate last week. The main reason was that we got some information from the ETA to not enter the SIs in the absences into the Educate, because some students were having some issues, connections issues or something. I'm not sure. I'm not sure if this was affecting any of you. I don't honestly think so, but just in case some might have had those issues, we were instructed not to enter the attendance. But right now, starting hopefully for this week, there's no more issues, and then this week we're going to take the attendance and enter them as in the Educate. I'll still keep the attendance as I showed you last time in the system, and I keep doing that for every one of the classes to monitor how many periods people attend. So that's the first announcement, but this is not going to be entered for the past 2 weeks. For this class onwards, inshallah, it will be. The second announcement would be about this announcement regarding the quiz. Now, the quiz one, as I have sent this to you, you might have seen that they're going to be next week on Tuesday. This is going to be at 10 a.m. period 4. In person means in the labs, and the male branch at these 2 labs, and the female branch at these 3 labs. Make sure that you are on time. That's very important, because many other courses have actually exams immediately after you, and they have quizzes as well in those same labs. So just be on time. The quiz is about half an hour, and the topics that are going to be covered are the ones from the week 1, week 2, and week 3, which is this week, what we're going to be covering today, inshallah. So the quiz is going to be on week 4. That means before we meet next week, inshallah, we meet at the same time at 3:30, right? So the quiz 1 is going to be at 10 a.m. in your respective branches. So be on time, and it should be the topics that are, as I mentioned from here. Actually, I'm using the pools. There are large questions in those pools, the same ones that I give you for the reviews, and I'm going to pick up the same again from the same pools. I'm just going to give you the questions for the quiz. That means if you do your reviews, if you'd like to get prepared for the quiz, just go to these mini test reviews and do these 1, 2. I see they're still available. I'm just going to keep them available until the end of the course. And immediately after this class, this one is going to become available. As you can see, it will be available today at 6:30 p.m. So after you finish this class, then this one is going to be available. And this is what we're going to cover today, inshallah, on top of what we skipped last time. This being said, any questions before we start? We're going to take class on that. Yes, they're going to be class on that day. Yes, the quiz is outside of the class time, and we're taking class. We're only losing a week, if you paid attention. Week 5 is lost for us because the national day is going to be on Tuesday, and then we're going to not meet on that day. That's why actually this has been adapted, so we can cover as much as possible, and there's no time for us to miss anything. So that means that also the mini test number 3. So I mentioned that this is going to be a review. Here I said this is review week 3. I did not call it mini test, because for the mini test, the mini test is going to be on week 6, right? So the topic that is going to be covered for the mini test 3 is always going to be the topic that we just covered the week before, which means those sets and set operations. This is what is going to be covered for the mini test 3. So every time you see mini test, that means it's going to cover the topic of the previous week. So that's how it works. So next week, inshallah, at 10 a.m., just make sure that you are in your respective labs. For 30 minutes, the quiz is going to be starting at 10 a.m. for 30 minutes. And the topics are from this section 1.1, 1.3, 1.4, 1.7, and 1.8. Only these ones. Okay, so this being said, last time actually we did not finish 1.4. There are some things that we did not cover. Actually, I also changed the slides because I added something that I found that in the exercises it's mentioned, but it wasn't in the slides. So I just added also this part. I just like to talk about it. And most likely, if you did your review for the mini test review 2, I also had already included the questions about these, even though we did not see them. And by the answers, you most likely would have understood actually what the topic, which is basically it's not something very complicated, but I just still need to talk about it. So this being said, let's dive in. Ala barakatillah. Okay, so last time we said that there are two these quantifiers. That means for every single one of the let's say if we read this over here, it means that every single x in the domain makes p of x to be true. Every single one of them. So if you have like the domain is 100 numbers, to check that this is true, we have to make sure that for every x in that domain, this p of x is true. So let's say we had said 100 and numbers from 0 to 100. Let's say from 1 to 100, that makes it 100 numbers. So I need to check that p of 1 is true, and p of 2 is true, and p of 3 is true. If one of them is false, then I cannot say that this is true. So this becomes false. So that's mainly the idea. But if I say the existence now, if I change this with the existence, that means there is at least one that actually satisfies, that makes p of x to be true. Which means that if I start by making p of 0, and I found that p of 0 is actually giving me something that is true, that means it's enough for me to say that the whole thing is true. Because I need to find at least one. This is what the existence means. So at least one that makes p of x to be true. That's what it means. With this, that means every single one of them, every single x has to make this p of x to be true. So that's the difference between the two. Now the talk about here is about the precedence of those quantifiers. Now we've seen the precedence that, if you remember, we said that the not is the first one. Then we said, what else? Do you remember? There's the and and the or. Which one comes first? Can someone remember? Oh, you said the not is the first one. Yeah, what about the is the and? The and then the or the or then the and? Okay, let me do something just to wake up some people. Which precedence? Which one has higher precedence? Yes. So and or after. I mean after not. I don't know. Okay, let's run this. Let's start. Let's get you activated. MashaAllah, I have 92. How comes? You're supposed to be 61 in one section. Oh, yeah, that's it. 61 and 31. That's 92. Exactly. MashaAllah. Okay, so overwhelmingly, there's the end. I hope that you answered without looking at the previous slides that you have in front of you. In that case, that would be great. Excellent. So, okay, I get it. All right. So we said, so it starts with the, we said not the end. Okay, where did it go? The, something is, oh yeah, I just select something, it seems. Okay, something is not working. All right. So let me fall back on my this one. So now I said this is going to be the, sorry, no, the not. And so we said the and or. Then if you remember, we have this if then if and only if. Now this existence, this quantifier existence and for all comes at the top, which means if I write something like this, sorry, p of x and p of q, or something else, let's say another q of x. Now what does this mean? Does it mean that I'm doing doing this and that, or the existence of this and that, the p of x and q of x? Actually, because we said that this is a higher precedence, if we don't have any parentheses, this is what it means. It's like if we have 5 times 2 plus 3. So if we don't put any parentheses, it's actually going to start with 5 times 2 plus 3, because this existence has higher priority than the end, and this is going to make this one to be, yeah, this one to be the first one to look at. If I want it to be these two, I would like to find an x that satisfies p of x and q of x, then I have to use the parentheses, because if I'm not using them, that's what it means. So this is basically, okay, discard, shift F5. So this is what we were talking about right here. Now there's the last thing is here, the uniqueness quantifier. Now if you might have seen that on some questions, there was some question about this symbol over here. This is how it is written. So now I'd just like to discuss what's the difference between this one and just the existence. So this is called the existence, this is called the uniqueness. The only difference is that the existence says that I need to find at least one that exists. There exists an x that means at least one among all the possibilities is actually available. I can have 1, 2, 3, 4, at least one. But here my condition is it has to be only one. So it's only one. I want exactly one. If I have more than one, this is not actually going to be satisfying what I want. The uniqueness quantifier, this is how it is. That means it exists, but only one. So this is how it is. So the main difference is that one, the existence at least one, and the other one checks at least one, and there's only one, at most one. So one is the minimum one, maximum one, which means one and only one. That's the only thing. So if I ask a question about something like this, which means I'm asking, is there for this to be true, I need to find among the domain where that x is, only one that satisfy the p of x to make it true. If I have more than one, that's the whole thing is false. And yes, so that's the thing. The last also part mostly is the negation of those quantified expressions, which just how to negate if I have something p of x. How if I'd like to negate this whole thing, what is it going to be? Now the negation of this basically is the following. If I have a negation of that means I'm looking at the existence of not p of x. And this is just like some examples. So let's have a look at this example. We would like to find this p of x is defined as x has taken a course in calculus. And the domain of these x's are the student in your class. So every student in your class. This is what I'm asking. So this means what? I'm asking here, I'm saying that for this to be true, that means every single one of the students in your class have taken the course in calculus. Has taken calculus. So what is the negation of that? The opposite of what I just say. If I say here, every single student has taken calculus. The negation of that is that not all students took the calculus, which means there may be some students who did not take calculus. And that's actually the negation of this whole thing. This is what it means. So the negation of the universal quantification is the existence. And the negation of the existence is the universal quantification. So that's the main thing. That's the main moral of the story. So these are just more examples and talk about that, and this is just showing you how and why, but actually I don't want to spend too much time on this because you have that, and most likely if you have any questions I would rather answer that. But this is the table that summarizes what we were talking about. This other thing, all the slides were just showing you the proof, how to prove that. But the idea is that if I'm negating the existence, I get the universal. But also this negation is transferred also to here, which basically what you need to, maybe if I can just write it this way, if I say this existence of x, p of x, this is going to be the same as the negation of the existence of x. I don't know if I'm just going to be a good way to write it, but I'm just try to make it in a way that's going to be easy for you to understand. So which means now this is actually for every x, and this is not p of x. So this is the idea. The negation of this gives us that. So that means the negation, you negate the existence, you make it for all the universal, and then the negation also has to go to the predicate. And that's pretty much it. And the same thing in the for the other way around. And so when is this true? So for every x, p of x is false. So here we say there exists an x where p of x is true. And if I say the opposite of that, that means it's not the case that there exists an x that p of x is true. That means all x that I have make p of x false. And that's what this means. So sometimes these phrasing can be a little bit confusing. So try to fall back always on the rule. And the rule is this: the negation of the existence gives you the universal quantifier for every x, and the same the other way around. Now these are just some examples. Now there is an honest politician, so let's do some negation of that statement. If I say there is an honest politician, that means if h of x is honest, and then I'm going to say that there is an x that is going to make that x is honest, and h is all the politicians. Now the domain is all politicians, and the domain here is all the politicians. Then the negation of that means it's not the case that there is an honest politician. If I say that sentence in that way, what does it mean? That means all politicians are not honest, they are dishonest. So that means this is actually going to be all politicians are dishonest. So that's what it means. And obviously they're talking about their on politicians. This is an American, I'm guessing, book, and the examples are from the American society. So, alhamdulillah, this doesn't apply to us all the way around, but it gives us an idea, anyways. So these are also some similar example exercises, and I hope that you checked some of them. I don't want to spend too much time on this unless you have some questions, because we still have two sections to cover later on, inshallah. And this part, which is the last one in the slide, in this section 1.4, translating from English into logical expressions, is just trying to find like these logical expressions that are allowing us to convey the same information that are in the words. And what makes it actually difficult is that there are many ways to translate the same sentence and to have the same meaning, and that's actually adds to the difficulty. And this is why actually these logical expressions can allow us to ensure, for example, that two sentences are equivalent, are the same, saying they convey the same meaning. And maybe some of this work is also related to artificial intelligence with automatic translations and things like that. But well, this is just some kind of examples on how this is going to be, for example, translated. So some students in this class has visited Mexico. So how can we convert that? We need to say that we need to take something, the subject, out of this to make the predicate. So let's say that the predicate is visited, and let's say X is the student. So the domain X is student, and then I'm going to say some students in this class have visited. That means there exists some X where v of X is true. So the X here is the domain is all students, and v of X is X all students in this class. Actually, I need to be clear, because not all students in all classes. All students in this class, these are the X's, and then X has visited Mexico. So that's the way how to do, one way how to do it. Another way is to have the X to be all people. So let's say this is the one way to do that. This get to this here. I think this is what they did here. Is has visited Mexico, and if the domain X is the students, and then if we're interested in people other than other in this class, but actually this is in this class. So this is just extending the example. If we wanted to do something more, if we just remove this and say some students has visited Mexico, then we need to have some kind of two predicates. The one that person is a student in this class, and that's visited Mexico as well. So they use M instead of. So the idea, this is basically just how we come to translate those into logical expressions, which we've been doing all along. I'm just going to stop here related to this. There's nothing more to do. These are some actually exercises on all of what we did before, but I'm not going to focus too much on that. And I hope that you actually what I did is that I uploaded these updated slides. I uploaded them to Blackboard. So every time you see something updated, you have to go here. Actually, maybe I should make a different system too, so you can find it easily. So if you go now to this one, this 1.4, I just updated it recently. I don't know if you can see maybe the time it was. No, unfortunately, maybe you don't see that. So you have to know where to click on it. Maybe I'm just going to add some updated and the date when it was updated. Similarly for the others. I added also, you can see this, I added 1.7, 1.8, but because 1.8 was not present in the list before, it ended up being in the bottom. So just pay attention to that as well. If you're looking for a slide of a specific section, you can maybe sometimes find it in the bottom. All right, so Discord. So you have all these exercises, and you can also go through by them one by one before look at the solution. You just see this, and then if you click on next, you can see the solution. So this will help you just practice by on your own. I'm just going to leave you with that, and let me close this and open the topic of today, the official one. Again, this is based similar on Dr. Abdul Salam slides. I'll just make some small changes to those in whatever I find it necessary, or maybe add some value. So what we're going to be talking about here is that proofs, how to make some proofs, how to prove things using the logic. Now we have also seen, maybe let me just keep that 1.4, because in that 1.4 I think we can go back to, oh no, this is not in here, that's the one before, the 1.3. Let me just open that. Sorry, 1.3. Yeah, that's the one. I would like to talk about this just because I remember the question that I was asked about from a student related to this. Now, is this important for you to memorize? Well, yes and no. Some of these you'll memorize them because you're going to use them and use them actually. Some of them make sense, so you just have to remember them. But the most important thing for me is that you understand them. Now, memorizing them is going to go with the practice. The more you use them, the more you're going to memorize them. Same thing that you don't need to memorize. Let me just maybe show you something from here. You don't need to memorize. Okay, what's going on? That's 5 times 2 plus 3 is actually, this one comes first than this one, the precedence, for example. It's just because you use them so much, you're going to memorize them, but you need to understand them. That's what I want you to do also for here. So for the quiz, I'm not going to give you a lot of things that we're going to write. All the quiz questions are going to be MCQs, multiple choices. They're just going to be, if I remember, with the same, it's 0.25 per question, which makes to 10, that makes it 40 questions for 30 minutes, which is, again, if you practice, these are the same questions that you might have find in the review. So if you practice, you understood, you'll be able to get them done in 20 minutes or maybe 15. Again, but for the midterm though, the midterm, I'm going to ask you to write things. So it's not going to be only multiple choices. So this is actually these things, you need to memorize them. While the question is yes and no. You need to understand them, but you need to know where to find them if you need to find them. Because this is actually something that I will give you, for example, to make some proofs and make some equivalences and prove those equivalences. So you need to use these and be able to understand how to move from one to another, and how to make use of them for your proofs, for example, proofs for equivalences or for anything else. So that's what I wanted to say before I forget. So now the thing is, I'd like to talk about these introduction to these proofs. By the way, I'm going to give you this mini test 2, where I'm planning to have it today, right? We did not do that. The mini test 2 about this 1.3, 1.4. I'm just going to give you that in a few minutes, maybe, inshallah. So once I started talking about this, I'll use it as some sort of a break, and then to move on, just after I introduce these proofs and what they do, and proof by direct proofs, and maybe proof by contraposition or by contradiction. We'll talk about this. So about these. So now the proofs are a way how to, we've seen, like, if we'd like to prove that two expression or compound prepositions are equivalent or the same, I need to prove them somehow. So the proof that we've seen is we use a truth table. So for example, if I tell you that, okay, if I would like to have prove me that if I do this P and Q, this is actually equivalent to Q and P. So how can you prove that? Well, one way to do that is to go for the truth table. This is what we've been doing. before earlier. So I'm just going to draw the truth table of P and Q, and then P and Q, and then Q and P, and then see that they are the same. And this is actually this is going to be the way to prove that these are equivalent. That means they have the same truth tables, truth values. True, false, false, true, and false, false. And this means this is going to be true, and this is going to be false, false, and false. Similarly, true, and then false, false, false. They are the same. Then I'm going to say, these are equivalent. So now another way is to actually go and use those here, those rules that tells us, this is not this one, this is called the cumulative laws, which tell us that if I have P or Q, this is equivalent to Q or P, and same thing with the AND. So these are some of the laws that we can just make use to prove that two are equivalent. Well, I mean, we could use other ways, but this is another one of the ways. This is what I tried to say. Resume slideshow. So another way is to have a different type of proofs that says, okay, I'm just going to look at the values and try to make sure that these are actually going to follow the same, some sort of a type of proof. Like one of the type of proofs is by doing this direct proof, which means that if I prove that something is true, then something else is going to be also true. If I this using some inference, that means I'm just going to assume that if this is going to be, for example, true in a specific condition, and then once I check that this actually happens, I'm going to say, then this is going to be true. Let me maybe, I feel like I was not very convincing. I'm just going to try by using this example. Now, give me a direct proof that if n is an odd integer, then n squared is also odd. So the direct proof means it follows this type of pattern. If P is true, then Q is true. So now P is what? N is odd. Okay, no, that's not good. I cannot erase it easily. So I said, okay, this is if this is P, then this is Q. And all I have to do is I'm finding myself that I have to prove that if P, then Q. So the idea is we're going to assume that the conditional statement, which is the P, is true. That means n is odd. Okay, let's assume now that n is odd. We know that if n is odd, that means n is going to be in that form. I can find, because it's odd, I can find a number, because we said n is odd. For any n, I can find a way that n can be written in something like this, like some kind of k, 2 times k plus 1. Now, you can try that. For example, 1 is odd. I can find that this with k is equal to 0 is going to be true. I'll say, okay, 3 is odd. That means this multiplied by 1 plus 1 gives me the 3. And so on. You can just test that for anything. This is actually one of the definitions that we can use. This being said, then by definition, the n is going to be that. So I'm going to assume that this is true, and I'm just going to replace the n with this k plus 1. Now, what I'm trying to do is to prove that 2k plus 1 square, why? Because I said n is square is going to be odd. This is my n. I'm just going to square it, and I need to prove that this is odd. And that's what I'm trying to do. Now, how am I going to do that? Well, basically, I'm just going to square that 2k plus 1. If I square that, it's going to give me, okay, I'm just going to make sure that this is 2k plus 1. I can multiply by 2k plus 1, right? I'm just going to do it slowly just to make sure that everybody is not getting confused. So that means what I have here is 4k squared. Then I multiply 2 by 1 plus 2k, and then plus 2k, and then plus 1, which gives us 4k squared plus 4k plus 1. So now this here, this value that this formula that I have here, I'm just going to use 2 and multiply this whole thing by 2, which gives me, this 4k is going to be 2 times 2k squared plus 2 times 2k plus 1. And then I'm just going to use the 2 and put the 2k squared plus 2k plus 1. Why am I doing the 2? Because I would like to find the same pattern that this is going to see some number n, not n is used already. Let's call it r. Okay, that's another number r. And that r is going to be 2r plus 1. And this is an integer. This is an integer. So I'm going to prove now that n squared with using this format is going to be also odd, because I have something that's multiplied by 2 plus 1, which is going to make it odd. And that's a way how to prove that if something is true, then something else is also going to be true. Let me maybe look at another example. I think there's another example. Okay, let's have another example using this direct proof. If m and n are both perfect squares, then m times n is also a perfect square. Okay, what is a perfect square? An integer a is a perfect square if there is an integer b such that a is equal to b times b. For example, 25 is a perfect square because it's 5 times 5. So this is a perfect square. And this, like 24, is not a perfect square. It can be like 6 times 4, but it's not like the same number multiplied by itself. So that's the idea behind those perfect squares. So that means you will find a number that is, if you multiply it by itself, it's going to give you that number. So now my proof is that I want to prove that if m and n are both perfect squares, m and n are both perfect squares, then, so this is going to be my P, then the Q is, then m times n is perfect square. All right, so we're trying to find now how to prove that if m and n are separately both perfect squares, then if you are multiplying them together, they're going to also give me the perfect square. And the perfect square is that one number is the result of the multiplication of the same number with itself. Now, what we're going to be assuming again is that we assume that m and n are perfect squares. That means we're going to find that there's some number which is going to make m is going to be s times s, and n is going to be a t times t. So any numbers. That means I found that because m and n are perfect squares, that means I will find another number s that is going to be, if I multiply it by itself, it's going to give me that m. And same thing with the n. This is the definition of this perfect square. So now the proof is, knowing these, I need to prove that mn also is a perfect square, which means I know that m is going to be s square, n is going to be t square. Now m times n is going to be what? I need to find something that gives me the same number multiplied by the same number. So let's try that. I'm going to replace the m with s square, and I'm just going to replace the t, the n, sorry, with the t square. Let's develop this. This is n s times t, which is going to be, if I move things around, times t times s times t, which is I'm just moving things just from places, which is possible because I can change the places for this is the commutative law of the multiplication, and we have something also similar to what we've seen before here. And then I can just now see that I have the same number, that if I'm this is a number, let's call it, for example, I don't know, w times w, and this is going to be this mn. I just proved that. Now mn is a perfect square because I found that there's a number that if I multiply it by itself, it's going to give me that mn. So this is actually an example of this proof. So this is the idea. So we just move things around by this commutative property, and then we just put this thing together with the associative property, which is going to give us then m times n is a perfect square as well. So that's the direct proof. We start from the first one. This direct proof is the following. We have the direct proof is having this format. Right? If P, then Q. We are going to assume that P is true, and from this we're going to find a way to try to prove that Q is true. And that's the idea behind these direct proofs. Everybody's okay? I don't know if you're still with me or maybe you need this is the time to take some small break, or maybe a little bit. Let me take this one, and then we'll take a small break and for the mini test too, inshallah. Now there's also another way, is that this contraposition, proof by contraposition, is that the proof by contraposition is that we begin with the premises, continue with the sequence of deduction, and end up with the conclusion. So this is what we did so far. We started with the premise, we did the hypothesis that this is true, and we continue some kind of deduction until we reach the conclusion. And sometimes this doesn't work, so we need to find another way, or sometimes that's not the easy way to do it. Not even not work. It might work, but that's not the easy way. So sometimes it's easy to prove the opposite than to prove it itself. So, and this is the idea with this contraposition. So we need to other method of proving theorem for the form something like this. For example, how do we prove that? So the idea is we're going to not do that directly, but find some kind of what's the opposite of that, and we try to show that the opposite of that is false. That make the thing true. And now why are we seeing this? For example, it's the opposite of this. What's this? The negation of that. The negation of that is this here. I wanted to write it, but then I found that it's here. So this proof by contraposition exploits the fact that in the conditional statement, the one that we use for the direct proof, this is equivalent to this contrapositive, which is the opposite of that. The opposite of that. I'm not going to the equivalent because this equivalent, remember, this has an equivalent which is not P or Q. It has also, this is part of what we find here. Yeah, this one. If P then Q, this is equivalent to not P or Q, and that's not what I'm doing. I'm doing the opposite of, it's a negation of P then Q. That's another equivalency, but I'm not doing that. But the negation of this is actually the negation of if P then Q is going to be not Q gives not P. Am I right? I'm not hearing anything, and I'm telling things that are false, and you just swallow whatever I say, and you agree with it. Is that the opposite of this? Or at this point you're just not with me? Okay, you know what? Let's take some break. You don't seem to be in shape, or maybe you're just thinking about this mini test too. So let's get on with it. So I'm just going to pause the video, the recording, and then the video recording is with this. Okay, let's resume. So what we were saying here is that, yeah, I was talking about over here. We'll talk about the proof by contraposition. Now, if you have any questions, I've seen some in the chat having questions about the mini test. I don't want to spend too much time on that. Just send me an email and with a lot of details as much as possible. Screenshot also are actually the best because they help clearly understand what's going on. And I'll try to get back to you as soon as possible. So now I'd like you to focus, because I was feeding you some wrong information and then you were not paying attention to that. So I was saying that proof by contraposition is doing something that the opposite, and I was showing you that this, actually the opposite of this is that, and that's not the case. It's clearly saying it's equivalent, and actually if we go back to here, yeah, it clearly says here that this is equivalent to that. That means if P then Q, that's equivalent to if not Q then P. And this is what we have here, if not Q then P. So these are equivalent. So now the proof, by the direct proof, is that we use this statement, this structure. We go from the P, we assume that P is true, and then we walk our way to prove that Q is also true. And that's the direct proof. The contraposition, the proof by contraposition, is that we take this and we get the equivalent of that, the contraposition of positive of that, the contrapositive of this if P then Q, it's going to be if not Q then P. And from that, we're going to assume then that not Q is true, and we are going to walk our way to show that actually not P is Q. And if we do that, that means we just proved that if P then Q, because they are equivalent. So that is the proof by contraposition. So what we're going to do in a proof by contraposition of if P then Q, we take not Q as a premise, as an hypothesis that we assume that it is true. And then we are going to go through differential laws and use some theorems and inference to try to show that not P must also be true. And then we are going to prove this, that this is true. And if we do that, we can just say, oh, because this is equivalent to if P then Q, so therefore, if we prove that this is true, that means this is also going to be true. That's the proof by contradiction, okay? So pay attention, please. If something's not clear, just write about it in the comments, the chat, and then so I can be able to just address your comment there. And the answer, if I got a lower than the second score the second time, yes, the second time is going to be the last one, the one that we keep. All right, so let's see some examples. Using this contraposition, I would like to prove that if 3n plus 2 is odd, then n is odd. So now P is this, 3n plus 2 is odd. And then n is odd, this is Q. So now this is in the form of if P then Q. Now, if I'd like to use the direct approach, I'm going to start from P, that is assuming that P is true, and then I'm just going to walk my way to try to prove that Q is true. Now, that's not what I would like to do. With contraposition, I would like to go for not Q, and from there, go and find out that actually not P is true. And that's what we're going to be doing. So the first step is then, I'm just going to start from, is to assume that the conclusion of the conditional statement, this conclusion, n is odd, is going to be false. That means it's the opposite of that. That means n is even. So I'm just going, this is not Q. This is Q, n is odd. This is not Q, because if it's not odd, it's even. So I'm starting from here. I'm starting from n is even. And then I'll try to find a way to show that actually not P. So this is P. What is not P going to be? Not P is going to be 3n plus 2 is not odd, which means is even. And this is what we're going to be trying to find out. Then what we're going to be doing, same thing, the definition that we use with the even and odd, is that we're going to start with this, assuming that n is, because it's even, we said assume that n is even. That means it's something like this. It's n is equal to 2k. And then from this here, we're going to replace 2k inside this n over here. Sorry, let's check it. So that means now this n is going to be the 2k, and I'm just going to go from there until I find this 6k plus 2, because this is what I get, 3 times 2k, that's 6k plus 2. And what I can do now is that I can do this same thing that I did to prove that this is actually 2 times some number, and doing that is going to show me that this here is going to be even, because it's a multiple of 2. So then I prove this is equal to 2 times something. That is going to be an integer. So that's how I prove that this is even. Now what I did, I just proved that if not Q, then not P. Therefore what it means I proved this. Therefore it means that P, if P, then it's Q. That means if 3n plus 2 is odd, then n is odd. And that's the way how this proof by contraposition works. So this is a negation of the premise of the theorem, and then it's just go from the other way around and prove that statement, starting from negating the consequence. What is it going to be? Another example. This one might be a little bit confusing, but we'll try to get it one step at a time. Now, assuming that we prove that if n is equal to a times b, where a and b are positive integers, then a must be less than radical of n, or b is less than radical or square root of n. Actually, I mostly use square root of n. So now, what is p? That's n. Sorry, I'm just going to write it this way. P is n equal a times b, where a is positive and b is positive. And then this one is the q, which is a is less than or equal to square root of n, or b less than or equal square root of n. That means not, I'm going to prove that starting from not q and walk my way out until I found that actually not p is going to be true. So what is not q? So I'm going to be not Q is going to be not this whole thing, which is what? This is, if I just do the negation, that means this is going to be A strictly bigger than square root of n, the OR becomes and B strictly bigger than square root of n. So this is what I'm going for. I'm assuming that not Q is true. I'm going to try to find out that not P is going to be true. So I'm just going to, sorry. So this is the first step, is that I'm just going to assume that this is false. That means I'm going to make this, the negation of this is true. The negation of this is going to be true, and then it shows you that the multiplication property and equality, I mean, yeah, this is something, I don't know, maybe we're going to use that later, I'm guessing. Let's find out. So that means this is equivalent to this. This is what I just showed with this, De Morgan law. And then we need to show now that this is not true. What is not true? That n is not equal to A times B. And so that this is what we need to prove now. So to be able to do that, what we need to do is to multiply these A and B's together and see that this should not be equal to this n. Now, if we do multiply A and B, we end up having square root of n times square root of n, which is going to be n, that is, that AB is going to be bigger strictly than n. If it's bigger strictly than n, obviously it's not going to be equal to n. And then this is not P that we were looking for. And we just showed up that starting from not Q, we found out that not P is true. Then we can say by contraposition that if P, then Q. And that is the idea behind this proof by contraposition. So the idea is that direct proof is we go from if P then Q. The proof by contradiction, we just go by from not Q then not P. Both of these are equivalent, but we just look at it from a different point of view because sometimes it's easier to do it one way or the other. And there's no, I mean, you should just find the way. I'm just showing you different ways how to do things. And based on different scenarios, you will find the best way to, or the easiest way to go. But you should also be able to go through any way. If, let's say, in the midterm theory, I'm just going to ask you, okay, using the proof by contraposition, use this. And if you find that, oh, I can prove that by direct proof, it will be much easier for me. But yet, because I'm forcing you to use the by contraposition, so you have to use by contraposition. So you should be able to be comfortable with all different types of proofs. And if I'm not asking you to use a specific way, then you can use the easiest way for you. So that's the idea behind this direct proof and by contraposition. The last one in this point 7, I think, if I'm not mistaken, is this by contradiction. Now the proof by contradiction is that we're going to try to, if we have a statement that is true, we're going to assume that that statement is false. And from there, try to prove that by contradiction, this is going to lead to some sort of a contradiction. And that means that it's going to lead to some Q that is actually always false. So that's pretty much the idea. So let's jump into an example, so it will be much easier to show that. So show that, for example, now we'd like to show that this is true. What I'm going to do, I'm not going to show that this is true. I'm going to try to show that this is false, which means that I'm going to suppose that this is false, which means that instead of being not equal to 0, I'm going to assume it's equal to 0. Because it will be easier for me to move things around and try to show that actually it's going to create some problems. So now if I'm going to assume that this is equal to 0, I'm just going to move things around, and that means that a squared is going to be equal to 4b plus 3. Same thing, we just take these, minus 3 becomes plus 3, minus 4b becomes 4b, and then that's what happens. So from this, then this RHS, I just almost forgot about it. This is the right hand side. This is the right hand side of the equal sign, and the left hand side, this is the left hand side of the equal sign. So this is just some kind of shortening of, if I like to see that this is right hand side and this is the left hand side. So what we find out here, if we look at these two, on the right hand side, this is something that is going to be 2 multiplied by k plus 1. Now we can prove it even directly by showing, let me write it here, maybe 4b plus 3. This is actually 4b plus 2 plus 1. So I can just take 2, and then this is 2b plus 1 plus 1. So let's call this my k, and this is going to be 2k plus 1. That means this here is odd. And on the left hand side, a square, a is odd. So it should be, something odd should be equal to something odd. And that's what is going to assume that this, because this is odd, that means a square also should be odd. Now if we also use the same type of idea, that means this, because a is odd, and a square, that makes it odd, but this here, I can write it with this type of writing, so because it's odd. And then that means replacing the a with this 2n plus 1, I get 2n plus 1 square is equal to this 4b plus 3. Keep the calculation that simplify this, remove the square, and I'm going to have this 4n square, well, just to make sure that we get that 2n plus 1, 2n plus 1, that's going to be 4n square plus 2n plus 2n plus 1. So this is going to be the 4n. How this is coming from? This here over here. So, okay, sorry. And then by just taking the 2 out of here, actually what happens, a couple of things happened here. So what happened here is that we put this 4n square plus 4n plus 1 minus 4b, and then we just take this, how to be equal to, if we take this one, this here over here, it's going to become minus 3, right? So this is going to be 4n square plus n, these two, plus, sorry, this is minus, this is, now I cannot make a, can I, yeah, I can maybe do the eraser, erase it, and then go back and pen, minus b, and then here this is plus 1 minus 3, this gives me minus 2. This is going to be equal to 0 if I move everything in one place. Now the other thing is that I can move this one to be the other side, and this is what I get. This here on the left side, this one on the right side. So this is where I get it from. So I just moved all of these from this to this side, to that side, and then I just factorize with the 4, and I'm getting this. Now I can simplify even more and take this 4 divided by the 2 divided by 4. So if I divide by 4 here and divide by 4 here, this is what I get. This gives me 1. This gives me 2 divided by 4, which is half. And this is going to be 0.5. And this actually leads to some kind of contradiction, because we said that these are going to be first integers. A and B are going to be integers, so it's going to, well, this is not the contradiction, sorry. So because the left-hand side has integers, yeah, this is where the contradiction is, because this is an int, and now this one is a rational, a fraction. So that means the contradiction, what we do is that we take something that we would like to prove, we assume that it's false, and we assume that the false is the correct one, and then we move our way to find that, we find some sort of contradiction that doesn't make sense. So we cannot make something that we said this is going to be an int, and at the end this int is going to be equal to some sort of a fraction. This is 0.5. So that's not possible. And that's the contradiction, which proved that our hypothesis that we assume that the proposition is false, that's not correct, which makes that this is actually true. So that's the idea behind the contradiction. We just assume that it's false and prove that this is going to lead to something that doesn't make sense, which is going to lead us to that our assumption that we first made was wrong, which leads to that actually what we had already was the right thing. Let's try another one. Same thing, we'd like to, by contradiction, prove that a squared minus 4b is different from 2. And then we are going to suppose that this is false. I don't know what this rectangle is doing, which means that we're going to suppose that a2 minus 4b is going to be equal to 2. And we're going to work our way into trying to find that actually this is going to be a contradiction. So now the condition statement being false means that there exist two integers, that a squared minus 4b is going to be equal to 2. And that's going to allow us to put this a squared is equal to 4b plus 2, which makes just this one, this minus 4b, we just put it on the other side. That leads to 2 times 2b plus 1 again, so that a squared is going to be something even, because this is the type of, this is something like 2 times k. This is going to be an int, and then this int times 2, that means the whole thing is going to become even. That means my a squared now is even. Since a squared is even, that means a is equal to something like this, for some letter c. And what we're going to do is that we're going to replace now this a with this 2c, and because we're going to replace this here, and we're going to see if this is going to make some sense. So now this a squared minus 4b equal to this one over here. We're going to replace it here. I mean, that's we just back to this one. We can also use it from here. It's not going to be much of a big deal, but it's much clearer when we do it from here. We'll see why. So now this a is going to be replaced by 2c, which gives me 2c squared, which gives me this 4c squared, 2c, the whole thing square, which gives me the 4c squared, minus 4b is equal to the 2. We just take the 2, to remove that, to simplify it, that makes it 2c squared minus 2b equal to 1. Therefore, then we take the 2 here, and we are going to take the 2 to factorize that. So we have 2 times c squared minus b, 2 times c squared minus b is going to be equal to 1. And there you go, we have a contradiction, because this is something to the form of 2k, which is normally should be even. And then we ended up with equal to 1, that is odd, so it's not possible. And since c2 minus b is an integer, it follows that 1 is even, which is not possible. So that's why something went wrong, and that what went wrong is our initial mention that the proposition is false. So the proof by contradiction is a different way. So now we've seen 3 types. The first one, the direct one, we're going to assume that if p is true, I'm going to prove, starting from p, going to find that the q is true. The contraposition is that I'm going to start by not Q is true and find my way until find that minus not P is true, which is going to be equivalent to what we were wanted initially to do. And the proof by contradiction, we're going to something that is true. We're going to prove that it's true. I mean, unfortunately, I just have to click here. That's too long. Erase. But let's do that. So I'm just going to assume that not P is going to lead to contradiction. And then by doing that, it proves that P actually is true. P is true. That's how I prove that P is true. So I'm going to contradict, do the not P, and then prove that the not P leads to some contradiction. And yeah, so I'm just going to skip this example because I would like to spare some time for this is also again same things. I'm just giving more examples so you can just maybe have a look at them. If you have any questions, we can address them, and then I'll show that. So this is maybe this one because I think I'm going to use it somewhere else in the next section. Let's talk now about this. Prove that square root of 2, this is square root of 2, is irrational. So what is irrational? That means we're just going to try to prove that, say that these two is rational. What is rational is that something is like a fraction. I can find two integers where this is going to be equal to that. So this is what this rational means. And when I say irrational, that means that's not possible. Square root of 2, you cannot find any two numbers that you can make the first one divided by the second one is equal to that square root of 2. So that's the idea behind prove that square root of 2 is irrational. And we're going to again do the same thing. We're going to assume that square root of 2 is rational, which means that we're going to find some a divided by b that's going to be that equal to this square root. And we're going to work our way from there. Basically, we're just going to square this. So that means this is going to be 2 equal to a squared divided by b squared. And then we just move the b. Okay, so maybe it's, let me just write it there. Right, it's called a, b. What I'm going to do is that I'm going to square the 2. So this gives me 2 equal a square divided by b square. I'm not sure if you send any writing, so nobody's writing anything. So yes, just raise the hand if I take too long to realize that you wrote something. So now this means that I'm just going to take this b and multiply everything by b square. So that means it's going to be 2b square is equal to a square. This is what this actually means. And now, by the definition of an even integer, it follows that a square is even. Because a square is even. Why? Because it's 2 times some k. In this case, my k is b square, but it's 2 times something. And we next use the fact that if a square is even, a must also be even. So that means we're going to say that there's some kind of c that we can find because a is even, that makes this a is equal to c. And then we replace that, this 2b by our a squared, that means like 2b square equal 2c square. This is what we did. We replaced the 2c in here, from this here, so we get that. That means 2b square is equal to 4c square. So this is what we have here. Then we just simplify this by removing the 2. Okay, that's not the best way. Let's simplify square equal 2c square, and this is what we get here. Which means our b square is even, and then that means, because it's of the form, it's to some k, in this case, k is c square. and that proves also that B is even. And now we found out that by doing that, we are saying that square root of 2 is equal to A times B that are both even. And normally, when we say that something is rational, that means the numbers cannot be simplified. These two have no common factors between them. Like, they're not on the form of 3 times something, and this one is 3 times something else, for example, or 2 times, or whatever number is, that they have some kind of common factor that I can have. These A and B's, because if we say that this is rational, if we assume that it's rational, that means it's in the form of A and B, where A and B, they have no common factors between them. And these are like the lowest terms that we can have. And now we just proved that they have something in common because they all have something of the form 2k something, and the other one is 2k something. So now we just run into a contradiction that's saying that initially we said that A, B do not have any common factors. And now we say, oh no, they have common factors, which is the 2, because both of them are even. So they have 2 as a common factor. And that's the problem. Then this leads to a contradiction, which means that now square root of 2 is irrational. That means you cannot find 2 integers that have no common factor between them that can divide that can represent this number square root of 2. And that's the proof by contradiction, to find out that, okay, this is irrational. Is that okay? Okay, I'm just going to skip those exercises. Since you have the solution to them, I'm just going to let you do them. And if you have any questions, inshallah, you can address them, send them to me, and I'll try to answer them as soon as possible. Remember, these topics that we're covering right now are part of the mini test, the quiz, right? Because we said the quiz one is going to be about all the 3 weeks before. That means in this one included. So the introduction to proofs, etc. You will have, actually, I made it that is going to become available, as you will see here, the mini test, here the review of week 3, which means include the questions about these two. They are going to be made available at 6:30 p.m. inshallah today. So just after we finish the class, normally I should have made them at 6. I think we can make them at 6, so you can try them. Let me test options. I'll change them, make them available at 6. That will be enough. I don't know why I put 6:30. So this is going to be available, so you should practice. All the type of questions, the pools from which I take those questions are going to be the same that you're going to find in the quiz. So you better practice a lot on these to make sure that you understand all the questions and you have less hesitation for the quiz. Now, one of the things why maybe you were having some, you've been rushed, is that I noticed that many of you did not take advantage of those mini tests. You don't practice them a lot. So if you don't practice and then you find that you don't have a lot of time to finish the quiz, then it's only you to blame because you did not practice enough. And these are the same pools. That means I'm not going to bring some different questions from myself. I might, but 99%, 90% of the questions are from here. So you have seen them before. And if you do enough test reviews, these mini test reviews, you'll be able to cycle through all the questions. So just practice, review doing those. Use these tools are for you to review and to help you check that you actually did not leave anything behind in terms of the understanding. All right, let's move on to the last part, which is this this 1.8 proof methods and strategy. This is something that I just used the same template that Dr. Abdesalam used before. And we're going to talk about these type of proofs, actually exhaustive proof and proof by cases, and then existence proofs and uniqueness proofs. So basically, something just, again, same logic, but this time the way we do things are slightly different. So I'm just going to maybe go straight to the example, so it's going to actually show you what we mean. Now, the exhaustive proof is that we're going to prove something by checking all possible cases. If we'd like to prove, for example, that this n plus 1 cube is bigger than 3 to the power of n, if n is a positive integer with n less than or equal to 4. So to prove that, what we need to do is to check for every n that is positive, that means 1, 2, 3, and 4. And for each one of them, we're going to prove that this is correct. If that's the case, that means we are checking every single possibility and we're confirming that it is true. If one of those possibilities is not true, that means this is not true. This whole thing is not going to be true. So now let's try. So for n equal to 1, we replace this n by 1. That gives us 2 to the power of cube. That means it's 8. 3 to the power of 1. That means it's 3. Is 8 bigger or greater than or equal to 3? Yes. So this is good. So this works. So for n is equal to 1, it works. Now let's check with 2. And we do the same thing. 2 plus 1, that's 3. 3 cube, that's 27, because it's 3 times 3, which is 9, times 3, that's 27. And then here n is equal to 2, so it's going to give me 9. 27 is bigger or equal to 9, yes. And let's do that with 3. 3 gives me same thing, gives me 64, and this gives me 27. Is 64 greater or equal to 27? Yes. And then I'm going to go for 4. 4 gives me 5 cube, which is 125. Is it bigger than or equal than this 81? Yes. Now, in all of these cases, we have seen that this works. So this method of exhaustion, that means we check every single one of them, and we can confirm that every single number, I mean, there's a problem here. It should be, discard. This should not be that, it should be here. The power. I'll try to update that, the file before. So this is by exhaustive proof. This is the proof, exhaustive proof. That means we are going to look for every single case, every single value, to make sure that every single value is respecting the rule that we say it's happening. Because it's different, slightly different from the cases, because for the cases, we try different things. Like, for example, the cases, like we got like proof that if n is an integer, then n squared is bigger or equal than n. So now what we need to do, we need to test for all n's that are integers. So, but it's kind of impossible to do an exhaustive proof with that. Every n, that means I'm going to start minus 900, well, I don't know how much, what's the integer, minus infinite, and then all the numbers until minus 1, until minus 2, minus 1, then 0, then 1, then 2, then 3, then there are an infinite number of values that I need to check, and it's impossible to do. But what we can do is, got some cases, we're going to try, okay, what are the possible values? We can have n is equal to 0, n bigger than 1 or equal, n less than minus 1 or equal. Unless, if we prove that for each one of those cases, this holds to be true, then we can assume that, okay, everything is going to be true as well. So that's the idea. So now let's try with the case number 1. That means n is equal to 0. So if n is equal to 0, 0 square, is it equal to 0? Is it greater than or equal to 0? Well, yes, it's actually equal, so this is true. For this case, I'm going to try now for if n is bigger than 1. If I have n bigger than 1, and then what I need to do is to multiply this to get the n square. N bigger than 1. This is my case I'm trying. So if I multiply n in both places, it gives me n square bigger than n for the n bigger than 1 or equal to 1. So I just proved just with this. For this case, if I just multiply n in both sides, it's just going to give me the rule that I'm trying to prove. So it just proved now for every number that is bigger or equal to 1, that n squared is bigger than n. Similarly, for the last case, if n is less than or equal to minus 1, then if I do this, however, it's in this case, however, n squared is going to be bigger than 0. So this actually, in this case, if we have n greater than or equal, less than or equal to minus 1, if I multiply by minus 1, what is going to be? Is this, if you multiply by n, that means n squared is less than or equal to minus n, which is not going to be actually what I'm trying to, and it's not the pattern that I'm trying to do, because actually this is not the way to do it. I'm not going to multiply this n and n here, because it does not give me the same result that I'm expecting here. But if I say n, actually n squared is always going to be positive, regardless of what number you give it. If the number is negative, n squared is always going to be positive, n squared. So if minus 1 times minus 1, that's going to be 1. Minus 2 times minus 2 is going to be plus 4. So minus minus becomes 4. So this is going to always be positive. So this n squared is going to be always positive. And because this is going to be positive, this n was smaller than minus 1. And n squared is bigger than 0. So n, this one is, if I would like to wrote, this is 0, minus 1, minus 2, etc. So n is going to be, I said, it's here. This is where my n is. And the n squared is going to be positive from this area. N squared somewhere here. I'm not, this is where n squared is. Because I said if n is negative, n squared is always going to be positive. So now, let me just put it again. That's why I don't like this. I said minus 1, minus 2. So I said my n is somewhere here. This is where n is. N is lesser than or equal to minus 1. My n squared is going to be positive for sure. So it's going to be either 0 or somewhere else. So n squared is always going to be positive. And because of that, this is also going to be true that if the n we said is equal to 0, it leads to this to be true. If the n was bigger than 1, it leads to this to be true. If n is less than 1, this leads to be true. Actually, it's bigger than 0, but we know that actually n is smaller than 1. So it's smaller than 0. Because n squared is bigger than 0, obviously it's going to be even bigger than n. So that's why they say that here n squared is still going to be bigger than n. So we follow a slightly different way for each one of those cases, but I'm assuming that n can be any one of these numbers in these ranges. And this is the difference between the cases and the exhaustive proof, because the cases I'm getting a range of values, and the exhaustive proof I'm making specific ones, all of them. And now I've proved that if n is equal to 0, this is true. If n is bigger than 1, this is still true. If n is negative, less than or equal to minus 1, then n squared is going to be bigger than 0, which is going to be bigger than n, because we have that n is smaller than or equal to minus 1, which is smaller than 0. So if my number is bigger than 0, obviously it's going to be bigger than minus 1, and it's going to be bigger than n. So that's why this holds as well. And that's the proof by cases. That means we take a situation, a set of possibilities, and then we look at all different cases. The case with it's 0, the case if it's less than 0, the case with it's greater than 0. Is that okay for these two, exhaustive proof and proof by cases? Any questions? Keep going. I should increase the time now. Right. Okay, great. Let's move on. We almost finished. A common error that we do with the exhaustive proof or the proof by cases is to incorrectly check every possible case. Now, if you miss some with the exhaustive proof, for example, or for the cases, if you miss some, then you are just going to assume that this is correct while it's not. This is very similar to what you do when in Java 1, for example, when you learn how to have an if else or if else if, you try to put all the cases in a way that is capturing all the possibilities. Now, if you forget to take some things into consideration and you just exclude some values, for example, in the case that we did before, if someone just checks that, oh, I'm just going to check if n is bigger than 0 and n is smaller than 0. Well, that's great, but you're skipping n is equal to 0. So if you can prove that, oh, for n is bigger than 0, that this is true. For n, for n that is smaller than 0, this is also true, but you cannot just say all n's follow this until you prove that for n is equal to 0 as well, it also does that. So you have to prove for every single case, and that's one of the common errors that you should avoid doing. And this is actually very important, and we use this type of proof to show that our program uses everything. And I remember, for example, I used to give an example, an exercise in Java 1 about the temperature of the water as an example of if, else, if, else. Now, the temperature of the water, it can be 0, it can be between 0 and 100. If it's between 0 and 100, this is going to be like maybe 0 not included. It's going to be liquid. This is going to be vapor, and this is going to be solid. So I'm just asking the user, okay, give me the temperature of the water, and then based on that, I'm just going to give you if it's solid, liquid, or vapor. And then if I don't pay attention to these limit values, for example, or don't set up my ranges properly, I might not check that my code works for every single type of value. I cannot test my code for every single value, but I can just put some kind of cases that rules, and this is the idea behind those type of proofs. Now, another type of proof is that we prove that something exists. That means many-theorem transitions that objects of particular type exist. So to prove that, that means we need to have that some of this type of form. This is called, I need to prove that there exists some x which makes this to be true. And that x that I find is also sometimes called a witness. That's something witnesses that this is true, actually. There are two ways how to look at this. There are some kind of constructive way and non-constructive way. And in the constructive way, we try to build and show that it exists. And the non-constructive way, which we do like this proof by contradiction. We just assume that it does not exist, and then show up that it exists or something similar. Maybe so that this existential, this existential quantification is going to be leading to, that means it's going to lead to some kind of contradiction. So something that is a contradiction. So let's find some examples that will clarify more what we mean. For example, a constructive existence proof. That means I'm just going to show that there is a positive integer that can be written as the sum of cubes of positive integers in two different ways. That means there is a way that I'd like to find a number. That number is going to be the result of a cube plus b cube, which is going to be exactly the same thing that I find some two other numbers, that c cube plus d cube. That's what I'm trying to find. Now prove that this thing exists. So by doing that, I'm just going to, if I don't, for lack of a better way, I'm just going to do it manually, one by one, try to find this. I mean, normally this is going to take a lot of time, so that's why they do some like computer program that finds that, and then we find that actually this number is actually the result of 10 cube plus 9 cube is going to give us that. If you don't trust me, you can just do it manually and check it. And also gives you that this is 12 cube plus 1 cube. 1 cube is actually 1. So this 12 cube, I assume this is going to be equal to that. If you want to try it, just you can try it. But the idea is that we need to find that there is a positive integer that can be written in that sum by finding one. This is the existence proof. I find one that actually follows that. And the way that I find it is that I actually do it, try to find it literally. This is the constructive proof. A non-constructive existence proof is that, like for example, so that there exist irrational numbers x and y such that x to the power of y is rational. Now again, remember this rational means if x power of y is rational, that means it can be some a divided by b, knowing that these can have no common factors between them. So the idea now, we've shown that this square root 2 is irrational. Remember that I said that we're going to use that example here. We proved it before that this was irrational. So we're going to work with that and then consider the number that is the square root of 2 to the power of square root of 2. If it is rational, so because they say there exists irrational numbers x and y such that we have this. So irrational numbers, I'm going to use this square root of 2. I know this is a rational number. And another for the y, I'm just going to use another square root of 2. And this is what I'm doing. So I'm assuming that, and we have two irrational numbers, x and y, with x to the power of y to be rational. So now what I'm going to do is that I'm just going to put that rational, so we can let this x to be square root of square root of 2 and then y to be the square root of 2. Why not? So on the other hand, if square root of 2 is irrational, I think I missed something. Consider the numbers. We said this, if it is rational, we have two irrational numbers x and y with x, y to be rational, and this is going to give us this. So this is the I'm trying to again to find the non-constructive existence proof. So I would like to prove in a non-constructive way that there exist irrational numbers x and y such that x to the power of y is rational. So these two are irrational and they lead to this to be rational. So what I'm trying to do is I'm trying to say that if it is rational, we have two irrational numbers x and y with making x to the power of y to be rational. And now this x is this and y is that. So this is one case. I think on the other hand, I think I have some issues also with this. I forgot actually about it. So on the other hand, if this, that means this thing, is irrational. Oh, okay. So if this is irrational, that means we can have now this x, why do we have this and why do we have that? So that, yeah, but where did this come from? Actually, I forgot about this. I don't know. I need to double check about that. Why did we choose? My point here is, why did we, well, for this thing, I understand it. We know that this is irrational. We use it here. That's fine. But here, on the other hand, this is irrational. Why? Well, I don't know. I'll get back to you on this. I need to check it again. I think I have some issues with this. Why do we use this one? But I get where they would like to come into. They would like to come into the fact that, I mean, this is actually from the book. That's why this is where I took it from. hold on, this is actually, let's go back to the book. 1.8. Okay, so let's have a look. Exhaustive proof, proof by leverage without loss, and there's actually more than exercises than that. I think I went to, no, this is more. Actually, I did not attach all of them. I think I skip it maybe here. It's going to be in the beginning maybe. Somewhere here. Common errors, okay. Existence proof, right. So this is for the constructive existence proof. This is for the non-constructive existence proof. So I say by example 11 in section 1.7, this is where we find that, yes, square root of 2 is irrational. Now consider the number, this, if it is rational, so we consider this number. If it is rational, we have two irrational numbers, x and y, which it is. Okay. On the hand, if it is irrational, oh, okay, so now I get it. So maybe the way I put it, actually this, let's consider this number over here. Let me put it a different way. It will maybe better. So let's have this number. Now I have two cases. The first case, if it is rational, so that means this here, let's consider this number. If we consider it to be irrational, that means we have two irrational numbers, x and y, that are going to be making this to be irrational. So this x and y are going to be this. And then on the other hand, if we say that this is irrational, now this one, we said if it is rational. No, let me just copy this, maybe it will be better. If this is rational, then we have two irrational numbers that have this property x to the power of y, and these two numbers are these ones. And then this is going to say if these are irrational numbers, which is fine. These are irrational numbers, which is correct. But on the other hand, if this is irrational, then we can try to find some way to put x to be irrational and this one another irrational, so that if we do the power, so square root of 2 square or to the power square root of 2, this is the first one, this is the x, and then this is going to be to the power of y. This is y. Let me just go back to sharing here. So this is the y, and then I'm just going to try to find out that if I say that this is rational, that this doesn't make sense, because if this, I say that this is going to be irrational, I just going to simplify that, and it becomes square root of 2 to the power of square root of 2 times square root of 2, which is going to lead to square root of 2 to the power of 2, which is going to lead to this 2. And this is the contradiction. So we found out that this proof is an example of non-constructive existence proof, because we have not found irrational numbers x and y, so that x power of y is rational, and that's the idea. We have shown actually this leads to something that did not work, not what we wanted to be doing. I know that I was not the smoothest here in explaining that, but inshallah I will try to come up with more examples next time maybe, or you can find actually better. Maybe I have included some exercise. I included some here after this. You have some exercise that prove maybe this is exhaustive, and this is you can use that with the cases, and I think this one is for the I mean this is the same. I did not include for those. Maybe I should go back. Maybe next time I might, but next time is the quiz, and that's why I want to find a way to want to open the book to find some more exercises or some more examples about that. A jump is a game. And this is even more, even more complex. I don't want to get involved into that. Yeah. So anyways, I'll try to find a better example, and maybe I'll upload it inshallah later. That will be the best option. So I'll try to find a better example that's simpler to understand, and I'll do that. And by the way, talking about that, maybe there's something already here. I included in the resources something that I found very interesting. This is from this person, Kimberly Bram. I don't know where she is from, but she's a doctor somewhere that teaches discrete, and it has some very interesting. So I've seen some of them. And you can see that it has a lot of these bisections, videos bisections, and we can find hopefully by disprove by existence. So she does not have that. She does have proof by existence and uniqueness. So she might have some things here. Maybe I'm just going to refer you to this one. Let me just copy. Can I copy? Maybe copy the link from here. Copy link address. I'm just going to put it right here. So it will be actually something that is going to explain more, because I will check it also as well. So maybe video to check, and let me just put that, make it a link. Where's the link? I'm not seeing it right now because I'm in a hurry. Yes, here. All right, and in the new window, that will be fine. So now hopefully you'll find, if it's not there, you can still get it from the resources. So I'm just trying to speed things up so we can move on to the last part, which is this proof by uniqueness. Okay, now the existence means we need to find at least one that finds it, or actually find one that actually prove the contradiction of it. We cannot find it, and then we prove that the opposite is going to be findable. Now the uniqueness is I need to find only one. So there might be more, but I need to prove that there exists and it's unique. So to do that, I need to let me go back here. So some theorems have said the existence of a unique element with some specific property, and then the theorems, they say that they have only one element has that property, and we need to prove that. Actually, how can I prove that only one? So we need to prove that first of all it exists, so that element exists, and then it's unique. So we need to prove its existence, and then it is actually unique. Now it can be shown into something like this, which might look a little bit complex, but let me try to simplify it a little bit. So notice first of all, I need to find that something exists, right? Something exists, but this does not mean it's unique. At least one. Now this here means at least one. So it can be 1, 2, 3, but at least one. But it doesn't mean it's unique. So what is going to make it unique is the rest of this. Now I want something to exist to make this to be true. And at the same time, and for every other number that you have that is different from that number that we just used, that we said they exist, that we'd like for every other number, that number is different from the x. If that number is different from the x, then this p of that number is going to be false. That means it's not possible to find another y, different from the x, that is going to make p of x to be true. If you find another number y, for every other number y that is different from x, this p of that number y is going to be false. This will make it unique. And if we'd like to write it in this in the way that we just said of the uniqueness, this can be simplified by doing this. I'm just trying to hold on. Let me find my pen. That will be easier. So this means I can just use this uniqueness. Exists a unique x that makes p of x to be true. This here is the same as this. So again, let me just try to make this clearer. This here says that there is an x, and that x has this property, whatever is in here. That property means that there's an x that makes this to be true. Now, at the same time, I want that this is going to be true for that x, and this p of x is going to be true, and for every this is another one. For every y that exists in the world, I want that if the y is different from the x, then the not p of that y is going to be the true. That means p of that y is going to be false. So not p of that y is going to be true. Which means that there is existing x that makes this to be true, and for every other y different from x, that will not make this p of that y to be true. So that literally says there exists only one x that is going to satisfy this p of x. Every other y different from x is not going to be satisfying this p of x. So it's going to be satisfying the opposite of the negation of p of x. So that's the idea. Now let's have an example, and I'm going to stop with that. I know that time is running out. Now show that if a and b are real numbers, then and a is different from 0, then there is a unique real number r such that ar plus b is equal to 0. So first we need to find that what is that r is going to be, if we just move things around, ar plus b equals 0, that means ar equal b, that means r equal minus b, that means r equal minus b divided by a. So this is the idea here. So now note that this real number is going to be this r that satisfies this, means it's going to be equal to that. And now, because this r is equal to this is what we say, r now is equal to this. We're going to replace this over here, which gives us this here plus b, and it's going to be, should be equal to 0. Now if we go and take the a and put it inside, we got minus we have a multiplied by minus b divided by a, which means the a is going to simplify. What we left off with here is just minus b, and this is plus b. This is what shows here, and minus b plus b gives us 0. And this, the real number, we showed that it exists because minus b plus b equals 0, so this is true. So we find out that there is a real number that makes this to be true. So this existence part of the proof has been done. We proved that this number exists, but is it unique? Now let's assume that we have another number s which is different from r, and that satisfies the same thing, because now we want to prove that it's unique. If we find that this s is different from this r, then we're going to say the uniqueness cannot be proven because we found another one that is different from here. But if we use this, that's going to make this again ar equal b, which is this rule over here, and we found this other s is also going to be equal to 0. That means the two are going to be equal, because this one we found that this is equal to 0. We assume that there's another s that allows us to do that, and this one is equal to 0. That means we need to they suppose that this as plus b is going to be, this second number is going to allow us to be equal to ar plus b, where r is going to be this minus b divided by a. And you've seen actually where this is going, and this is going to lead to remove this here. A is going to be the same thing, ar is equal to as, and then again simplify more. This gives you that if that second s number exists, that second number is going to be equal to r. That shows us that it's actually a unique number that exists. There is no other number that is going to satisfy the same property. So we proved the existence, and then we proved the uniqueness. That's That's basically what it is, this type of proofs. So now we've seen, let me just go back. We've seen that we have this, hold on, where? This exhaustive proof where we check every single one of the values, and they have to, it has to, each one of them has to lead to a positive outcome. That means this is going to lead to the, say that, okay, this works for the number 1, it works for number 2, so that rule works for every single number of the domain. Now sometimes if the domain is limited, it's easy to do. Sometimes when the domain is limited, then you go by cases. You want this to be bigger than something, less than something. You take all the cases into consideration. And then the existent proof is that where we prove that actually something exists, and the uniqueness is we'd like it to be not, it exists and it's unique at the same time. So it's exists and it's unique. And remember, we have this exists and unique, we have this representation of it. If you don't have, if you don't like this one, you still can use this existence of P of X, and there's also for every Y, there is going to be the Y, if the Y is different from X, then it's going to give you that not P of Y is going to be the true. So that's actually this whole thing just represents the uniqueness of X that satisfies P of X. There's some, I left some exercises here that you can just maybe have a look at, and unfortunately we don't have a lot of time left. I would like to stop in here. You can just go for these exercises. I have mainly put 2, and then different case 1 and case 2. You just do that, and if you have, also have a look at that video. This is very important because I think I was not clear enough in the explanation of this proof of existence and uniqueness. I think this video can probably help you more. Do you have any questions before we stop in here? This time you're very dry on questions. I don't know, because maybe you're busy, or you checked before, or you've seen the videos of this before, or you're too tired to pay attention, or I don't know what's going on, but I'm not actually very satisfied of the level of questions that I got. Anyways, if you think of questions, I strongly advise you to send emails. Remember, next time, when we meet, inshallah, you will have finished the quiz. The quiz 1 is going to be the quiz 1 is going to be inshallah on Tuesday next week at 10 a.m. Just make sure that you're on time. And yeah, this being said, Khalid, can we have highest grade in mini test? No. Inshallah, you have to practice more so you can get the highest grade without doing it more than once. So I made things available. Now, right now, I think you should be able to see that in the mini tests, this review week 3 is available. Just do the test, do this review many times. The more you do, the better you're going to be, because multiple questions are going to come randomly up to you. And then you have a large number of questions, and at some point you'll be able to cycle through a lot of them. So a big percentage of them, and this is going to make your quiz much easier. So do that for all these, because the topics of all these review, mini tests, and weeks. Actually, I should maybe do something called this review of week 2. That would be actually a better naming. I'm just going to call it review week 2, review week 3, and something like that. So I suggest you do that and repeat them many times, because the questions are going to be different every time, mostly. So then you'll be having a good exposure to all the questions. Again, the midterm is going to be for half an hour, and then the 40 questions, 0.25 each, like in the mini tests. So that means if you hesitate too much, that means you did not review enough, and this is going to cost you some grades. So why do that? Well, you have actually the same questions showing up to you. It's just now you have to do them quickly, and remove the hesitation. And the only time you hesitate if you're not sure. So I want you to remove these insecurities or not being sure of something, and you can only remove that by doing a lot of exercises. So do the exercises. Also, I advise you, I forgot to mention that, I advise you to use the book. At the end of every section you have a lot of exercises, and actually this is end of chapter material. These are the exercises, maybe, where no, this is the material. So the exercises before that, so this is for the section 8, and you have these exercises, and these exercises you have the solution to them somewhere in the answer to odd numbered exercises. So every number, odd number, this is 1, 3, 5, etc., you have the solution to those in the back. So every section, you go to that section, you would like to get the solution, you can get it from here. And then let's say section 1.8, you can just navigate through that and just need to find it. I don't know if I skipped it or not. Yeah, section 1.5, 7, 1.8. See, you have all the solution here. And for all of the others, actually it's a good idea that you do those exercises and you compare them to here. This is the best way for you to actually practice for each one of those sections of the chapters. Now, if you don't have any questions, you're free to go, inshallah, and wishing you all the best for the quiz, and see you inshallah next week. Can we send the book in the Blackboard? Not sure I'm allowed to. I'm not, because of copyright thing, I'm not allowed to put the book available for everybody. So yeah, maybe a section of it. I need to double check it actually for the section of it, maybe part of it, but it's not easy for me to do that right now. But I could check first. I need to check. Can I change the time? What time? Time for what? Shams, what are you talking about? Time for the mini test or time for the quiz? Time for what? Well, honestly, I don't want to change anything. If you're talking about the quiz, the time of the quiz is enough if you do the review, because I want also to make things easy for people who do the review. So if you review and I give you all the material to review, you should be able to practice that. And then if you practice enough, I would like to give also the opportunity to those who practice more to get more. So I want to be, fair to everybody. So if you practice more, you should get more. And if you spend more effort, you should get more effort. Somebody's raising his hand. Yes, somebody's raising his hand. Okay, go ahead. Someone want to talk? Just go ahead and talk. I don't know if someone really wants to talk, or maybe this is just something that sticks there. Or someone did it by mistake. I don't know. Yes. If you want to talk, just go ahead. We can see the microphone, but I think it's not working. So maybe the microphone is not working. I cannot hear. Do you? Do you hear? Okay, hold on. Maybe. Okay, 1 minute, because I did something, and maybe this is the. Let me stop the recording.